This project is a real-time vision accelerator built on a diligent Arty A7 FPGA. The camera, the 0V7060 is connected directly to the board, and the board captures, processes, and transmits the entire frame image without a CPU or operating system on the FPGA. What you see in the dashboard is the result of that complete live hardware path. This is the power, this is the Ethernet, both connecting to my laptop. And on the dashboard, under the setup, we can kind of begin to go through this flow. This kind of confirms that the verified bit stream is loaded, the camera and Ethernet link are healthy, the processing core is locked at 200 megahertz, and the laptop can properly communicate. There's also information about the switches and the buttons and how to kind of get rid of maybe a sticky error. And we have one-click programming as well. So basically, there's already an M7, which is the most latest milestone bit stream already in the repo. You can effectively just connect the RDA7, the Ethernet, and power, and you should be able to just click this button and it'll automatically program your board. Once it's programmed, it'll do a quick UDP check, which is when milestone 4 was when we introduced the Ethernet, so the check is done there. There's also simple, overrides to kind of start and stop, and it does exactly one. It verifies the bill ID and also whether or not the core is locked. Okay, and now this is where things can get a little bit more fun. If we go into the live section, we'll be able to effectively show what this FPGA can actually do. So first we can start with a grayscale diagnostic, and it should be streaming whatever my camera is. So if I put my hand over it, you should be able to see a grayscaled version of my hand. Same with my face, and same with my monitor over here in the corner. So if we're trying to figure out, exactly where does the brightness change sharply in the image, we can go over to reference Sobel. And Sobel is basically just a small edge detector. For every pixel, it'll identify, it basically takes a 3x3 matrix or a neighborhood, including the pixel itself, and then also the 8 pixels around it effectively. And then it does a weighted comparison based off of the pixels to the left and to the right, and then it corresponds strongly to the vertical boundaries. And then there's a second comparison which does GY. The vertical comparison would be done using GX, and this will compare the top and bottom, so it corresponds to the horizontal boundaries, if that makes sense. So this is basically exactly what's happening currently, and the design effectively takes the absolute strength of both of those gradients, and then it'll add them. Little changes will produce, dark outputs, as you can see in the middle of my palm, if I can position it correctly. And sharp changes produce a bright output, which you can see around my pinky over here. And this is why, flat parts of the screen mostly disappear, while the outline of the object, my hand, and other strong boundaries will remain more easy to see. Like as you can see, my palm here kind of blends in, but my fingers over here will kind of pop out. So if I bring my phone over here, let's see, there we go. Since there's a reflection on my screen, you're actually able to see the edges off the reflection, but if there was no reflection, or the places where there isn't a reflection, you can see it kind of blends into the back, but the edges and my fingers, which are actually holding up the phone, kind of feel appeared, and that's because they're brighter. And that's kind of the whole point of reference Sobel. So now, this may look a little weird, but now we're on threshold of Sobel, which is basically just reference Sobel, but we're adding a little bit of a threshold, right? So if an edge strength is below a selected threshold, here it's 96, then it automatically becomes black. If it reaches the threshold, it becomes white. Raising the value keeps only the stronger boundaries, and then lowering them will keep more detail, if that makes sense. The threshold is locked at a frame boundary, so one frame can never contain two different settings, right? So if I put my hand here, as you can see, nothing appears. Why? Because the threshold is too high, right? You can see maybe certain pixels where it's really bright. But if I drop this and I rerun it, you'll be able to see a lot more, because now the threshold for it to be white is much less. And you're kind of able to make out my hand here. And you can definitely make out my monitor, which has some very bright characters on it. If we drop this even further, maybe to 16, we'll be able to see a lot. And if we drop it to basically 0, everything will be white. Okay, and one last thing that we have to do is kind of just discuss about the integrity gate. And the integrity gate is basically just how do we validate whether or not the packets and the frames that we're getting from the Ethernet that go into the computer are actually valid. And mainly the way we do this is by just splitting the completed pixels into UDP packets, and then that specific split is written in RTL. And then when we send it over to the Ethernet on the receiving side on the laptop, we effectively just check the order that the packets have arrived, the dimensions, sequence numbers, and do a quick CRC check before displaying the frame. We can go into specific controlled benchmarks. I ran a quick shakedown, which only does 300 frames, and you can get artifacts automatically created, so you can see the specific frames and the logging in that if you really wanted to. Yeah, this specific run shows that, FPGA over OpenCV ran almost 7 times quicker, which obviously will make sense. And we also have 0 integrity errors, which is kind of the most important part to make sure that all of these frames are done properly. Right? So feel free to check this out. It's an amazing project. I feel like in the future you can probably run some sort of CNN or some sort of visual classification model on this and be able to specifically pick out specific edges or patterns of edges to kind of identify maybe moving parts in an assembly line or defects or things along the lines of that, maybe even navigation software. Obviously, this was kind of more of a personal project to kind of get used to the Arty A7, as well as trying to understand how much better running things in custom RTL on an FPGA are compared to just running software, which again, as we can see, much quicker, but obviously a lot more intensive to actually start and create. So hopefully this project will continue forward, and I'm looking into actually living out one of those defect detection type extension projects based off of this, but there still needs to be some more optimization and perhaps a better camera to run up to higher FPS, and also maybe gigabit Ethernet